Thank you, Eugenie. I'd like to thank the organizers for asking me to speak. So the title I posted was Perverse Sheaves on Compactifications of Locally Symmetric Spaces. The organizers also thought it was a good idea that I give some semi-expository remarks about compactifications of locally symmetric spaces, and I'm more than happy to do that. I think it's really appropriate for this conference. Locally symmetric spaces are some of the oldest and most studied moduli spaces, and so I think this is a good idea. So it's not clear how much I'll get to about perverse sheaves, but I'm going to try to. It's what I'm going to do, if I can get there, will be just talking about some work in progress that I'm doing, and it'll be in a somewhat informal vein. So let me begin. So we have to start with symmetric spaces. So let's start with D. I'm going to write it as G mod K. This is going to be a Hermitian symmetric space, but in point of fact, non-Hermitian symmetric spaces will play a very important role, but leave that in the background. So here G is a semi-simple Lie group, and K is maximal compact. So this is a Hermitian symmetric space of non-compact type. So examples. Well, how about the Siegel generalized upper half plane? So matrices, G by G complex matrices, which are symmetric, and for which the imaginary part is positive definite. And so in the case for G equals 1, then what we are actually getting, of course, is the standard upper half plane. And in terms of representing it as a quotient, so the generalized upper half space is the quotient of the Siegel group, of the symplectic group, modulo the orthogonal group. So these are 2G by 2G matrices in R that leave invariant a non-degenerate alternating form, and you can embed the unitary group in it as a maximal compact. And when G equals 1, this is actually isomorphic to SL2R. So please interrupt me at any point with questions. Yeah, I know, but, well,
Can you tell me about the wonderful compactification?
No.
Damn.
Asked and answered. So, locally symmetric. So I already have lied. Yes, G is a semi-simple Lie group, but in the back, what I'm really thinking of is there is a semi-simple algebraic group defined over the rational numbers, and G is its real points. So given that, we have the notion of an arithmetic subgroup. So gamma is a subgroup of the rational points of G. And rho of gamma, I'll define rho in a second, is commensurable with GL big N of Z. So here rho is an embedding, a faithful representation of G, or actually the underlying algebraic group, into some large GLN, and it's faithful, and it's defined over Q. So for example, you could just take sp2g of Z. Or in the case of SL2R modulo SO2, you could just take SL2Z. Okay. And so then we have X, which is the mod gamma, and these are the locally, it's a Hermitian locally symmetric space. So in our example, if we take the Siegel generalized upper half plane modulo sp2g of z, this is commonly denoted A sub g. This is a moduli space. But let me actually start first. What if we take the usual upper half plane modulo SL2Z? This is the, well, this is M1, or M11, right? M11, the moduli space of elliptic curves over C. And here, this is the moduli space of abelian varieties of dimension G, abelian varieties with a principal polarization. So these are, basically these are you take G-dimensional complex space, you mod out by a lattice, so it becomes compact, and then you have to impose a condition so that this is actually a projective variety, so those are the Riemann conditions. So these are two of the examples. And if you, for example, if you're interested in Hodge theory, the moduli space of most kinds of Hodge decompositions on a vector space will be given by an arithmetic locally symmetric space and many others. And I'll note that already this ties in with some of the moduli spaces that have appeared more often in this meeting. If you look at the moduli space of genus G Riemann surfaces, algebraic curves, then there is the Torelli embedding into AG. That takes a curve and sends it to its Jacobian. And so one approach to trying to understand MG, and not an easy approach, is to try and understand its image inside of AG. So it's important then to understand AG better. Okay, so these, in general, these locally symmetric spaces are non-compact. Algebraically, there's a condition on the underlying algebraic Q group that says that this will be compact if and only if the Q group has Q rank 0. And all the examples I've given, this has Q rank G and this has Q rank 1. So we're dealing with non-compact spaces. And we like to compactify things. For a variety of reasons, but usually the compactification will help us understand the internal structure of the moduli space. And in addition, the compactification might generalize the moduli space. It might generalize the things we're taking the moduli of by adding on some sort of degenerate objects. Or that might be useful for technical reasons, for doing analysis. So I want to briefly talk about three compactifications. Well, not so briefly. Compactifications, yes. And you can think of these three compactifications as the natural compactification to take depending upon what category you're in. So there's X bar. This is the Borel-Sayre compactification. And this is a manifold with corners. Real analytic. And this is, in some sense, a topological compactification. The point is that x bar is, in fact, homotopy equivalent to x. So you're not changing the topology at all, but you are turning it into a compact space. And then there's a compactification. I put a hat on. There's different notation in the literature, which is now called the reductive Borel-Sayre compactification. This was introduced by Zucker and without a name and simply denoted by Y. So what is this? Well, this is more of a differential geometric compactification. And the point here is that the metric, I haven't said anything about metric, I'll say more about metric earlier, but obviously on a symmetric space there is the symmetric metric. You can just think of it as picking a metric at one point and then pushing it everywhere under the action of G, and that descends to the locally symmetric metric on this quotient. And in the reductive Borel-Sayre compactification, that metric extends to metrics on all the strata. So this is the largest compactification where you can make that statement. And then there's, in this context, there's x star. This is the Bailey-Borel. And this is the algebraic geometric context. So if you're working in algebraic geometry. So what's happening here, this is a manifold with corners. Here, the corners are sort of crumpled down. It's a real analytic space. This is an algebraic variety, a complex analytic space. So it's in fact a projective algebraic variety, complex algebraic variety. But it's actually defined over a number field. But it's singular. So I want to try to briefly outline how you get these compactifications to give you a better feel for them. And to do that, you need to use parabolic subgroups. So what's a parabolic subgroup? Briefly, basically, think of a parabolic subgroup as a block upper triangular subgroup, but then maybe you take a conjugate of it. Let me be a bit more explicit. I'm going to assume that our group G is sp2G R, as in our main family of examples here. So now, so what did I say? I said this is going to be, okay, I might sometimes use G, not only for the genus, but also for an element of the group. But you'll forgive me for that. So G is leaving invariant, as I said, a skew-symmetric non-degenerate form. Let me pick this one. It's not the usual one you see in the literature. 0, 0, and then a diagonal of 1s, but the other diagonal. And so first, let me draw a picture of what is a standard maximal parabolic. So you pick G prime less than G. And the good way to think about parabolics, maximal parabolics, is you think about finding a one-parameter subgroup. So here's the one-parameter subgroup I'm going to be using in this case. I'm going to call this AP. So I'm trying to define what P sub G is, but I'm also going to write that as just P. And it's basically this. So this is a 2G by 2G block in the middle, which I put the identity in. And in here, which is 2G prime by 2G prime, and this has size G minus G prime, G minus G prime. I just have A times the identity, and here I have A inverse times the identity, 0 everywhere else. And so A is going to be an element of the positive reals. We get a one-parameter subgroup. So technical point, if G prime equals 0, so you actually should be using A to the 1/2 times the identity in the block. But let's just say that. And then how does that give you the parabolic subgroup? Well, on the one hand, you look at the centralizer of this one-parameter subgroup, and I'll put that here, the centralizer. And what will that centralizer look like? It'll also be block diagonal. And in this block will be a copy of sp2g prime. And in this block will be a copy of GL, SL G minus G prime, but I put plus and minus there. The determinant can be plus or minus 1. And then here is some matrix that will be essentially that matrix where you, do I have that right? Yeah, so you put whatever belongs here to make this whole thing be in sp2g. And what it is if that matrix is A, you take that matrix, you symmetrize it through the origin, okay? You just reflect everything about the origin and then invert it, and that's what belongs here because of this particular way of writing our form. So the advantage of this is everything's going to be upper block triangular, unlike the usual presentation. Now, so this is what I call MP, and as you can see, it's the product of two groups, MPL cross MPH. And this guy, that's the SL plus or minus term, and this is the sp2g prime term. So you have the beginnings of another Siegel generalized upper half space here. And then over here is going to be the upper triangular blocks. I mean the strictly upper triangular blocks. So identities on the diagonal and arbitrary up above, except you still have to impose the conditions that you're in the symplectic group. These are unipotent matrices. This is called the unipotent radical of the group. So you have this three-factor decomposition. This is called the Langlands decomposition. And such a decomposition would exist for any Hermitian, for a maximal parabolic of any Hermitian locally symmetric space, not necessarily this one. I would just hide all those matrices and write NAM, including this decomposition into a Hermitian part and a linear part. Any questions? Okay, so how do you use that to compactify? Well, I teach linear algebra a lot, so you first of all want to apply the Graham-Schmidt process. So what Graham-Schmidt tells you is that any invertible matrix can be written as an upper triangular matrix times an orthogonal matrix, which comes down to G equals PQ in this case. So therefore, that parabolic subgroup acts transitively on the symmetric space. So therefore, D, which is G mod K, is really alternatively written as P mod K intersect P. Now we can take that decomposition. The K, the compact part, only enters into that third factor. And so we see that we can represent our symmetric space as a product NP mod AP mod D sub P, where this is the quotient of that MP by its maximal compact group, and it breaks into a product of a dp linear cross a dp Hermitian. So before I get to actually compactifying, this is a good spot to talk about the metric, since that's one of the words in the title of the program. So metric. So these are great coordinates to be able to describe the metric, and the metric looks like the following. So first, what I have to point out is the following, that the subgroup AP acts on the Lie algebra of NP. Okay. I should have pointed out this is a semi-direct product with NP being the normal subgroup. So you can act by conjugation, the adjoint action. Let me write that Lie algebra script NP. And so I can decompose that Lie algebra in terms of the corresponding weights that this torus has on that Lie algebra. So I can write this as a sum over mu greater than 0 of NP mu. And so explicitly in our example, if you just think about the weights of the diagonal torus in SLN, you know that all the positive roots are going to be in the upper half. And so what are the corresponding weights here in the unipotent radical? Well, up here, it's going to be the entry here, which was A, times the entry here, which was the identity. So that's going to have weight A. And then similarly here, this is also A. Yes, it's identity times the inverse of A inverse. So, sorry, A here. And then this is going to be A squared. So going to be two possible weights. And again, if G prime was 0, now if G prime was 0, this inner block would become a point, these two would disappear, and that would turn into just an A. Okay? So you have those weights, and then here's the metric. I think this formula was first written down by Burrell back in the 60s in the Duke Journal. So the metric, the locally symmetric metric is, well, dA over A squared plus ds squared on on dp plus sum over the weights of some metric on this part of the tangent space. So some metric on NP mu times a weight factor, which would be A to the minus 2 mu. Except that's wrong. That's wrong. And it's a point that I'll bring up every now and then. This metric is going to be changing depending upon M belonging to dP. So as you go off to infinity in this piece, that metric is changing. So of course, if you restrict yourself to M belonging to some compact subset of this, what's going to turn into a stratum, then you can remove that dependence on M and you get what is commonly called a worked product. But out near infinity, things change. And then, of course, if you let R equal log A, also write this as dr squared plus ds squared dp plus summation e to the minus 2 mu r times ds squared of m. And this is on the nose. This is on the nose, not a quasi-isometry. These things, well, I mean, there's some choice, right, in the locally symmetric metric. You do have to pick a metric at a point. If you pick a metric at a base point so that the factors are orthogonal, they'll remain orthogonal, and you'll have this formula.
So the dependency on G prime is included.
There should be a G prime on each one of these. Okay? And then, yes, so this P, say I wrote P equals, thank you, Anda. P sub G prime. But for short, I'm writing it P. And so everywhere, everything I'm doing now, there's a G prime inherent in it. And so this is that SP, in this example, this is SP to G prime, and this is in the unipotent radical. Thank you. Other questions? Okay. So that's, yeah?
Is this metric, so this is some sort of bundle metric, right? Do we know anything about
There's no bundle yet. I haven't taken quotient by the arithmetic group, so this is an honest product decomposition. And there you have, and there you have it. Yeah, there's no bundle yet. But you do have to decompose the tangent space of this unipotent radical into its weight spaces. And this is only for maximal parabolic, so we're not looking at the corners yet. Okay, so I should say something about the corners. So let me put that up there, because there's subtlety.
Before you raise this left,
This one, yes.
yeah, are we expecting to see some maps occurring between those things? Should I watch for this as we go further?
Yes, there will be maps. All I've done is talked about parabolics and the space. I haven't done any of these yet, but the most obvious one, just to looking ahead, the most obvious one that'll come out of this is X bar. And then I will tell you how to get these by collapsing certain things on the strata.
There would be surjections.
These will be, yes, these are all surjections, and X itself will be within them as open, dense open subsets. Yeah, thank you. Other? Okay. So, non-maximal standard parabolic. Let me just draw the picture of one example. P equals P sub G1 prime G2 prime, where G1 prime is strictly less than G2 prime, which is strictly less than G. And so, block upper triangular, there's going to be more blocks. So now I'm just going to copy that, except I'll put blocks in like this. So let's see, this center thing is, 2G1 prime, and then this thing is going to be G2 prime minus G1 prime, and then this last thing will be G minus G2 prime. Those are the widths, and these are all square blocks, so you correspondingly have the heights, and then these two blocks have the same size as those two. And so this is the unipotent radical n sub p. And you have to figure out what are the conditions that the symplectic group imposes on those elements. And here's a little more interesting. Again, that central thing. So here's the identity, and get this right, yes. Here we have A1 times the identity, and then here it's going to be A1 times A2 times the identity, and whatever is the appropriate thing, just the inverse of A1 here and the inverse of A1 and A2 here. And that's going to be our split torus. And note here now, this is isomorphic now to two copies of the positive reals, with the coordinates being A1 and A2. I'm picking, the reason I didn't just put an A1 here and an A2 here is I wanted to basically these correspond to simple roots acting on AP, giving us coordinates. Simple roots for what? Well, again, this guy has an adjoint action on the Lie algebra of this guy. They're not really roots, but everything can be written as positive or non-negative linear combinations of certain simple weights, and the values of the two simple weights will be A1 and A2. And then the MP, well, you're going to have an SP2G1 prime, and then here is going to be a SL plus or minus of whatever I said it would be. G2 prime minus G1 prime, and then an SL plus or minus G minus G2 prime, and then the corresponding things here. So now, again, you have a decomposition into a linear part and a Hermitian part. The Hermitian part is that central square, and these two squares go into the linear part. So now you have to draw the picture, though. Oh, and I suppose I have to put the same sort of little caveat over there. If G1 prime equals 0, you have to replace A1 times the identity there by A1 to the 1/2 times the identity. And similarly, up here, A1, A2 identity by A1 to the 1/2 A2 times the identity. That's so A1 and A2 will still be the right coordinates, and they have to be the right coordinates. So now I can now I can start defining a compactification. Now let's define x bar. This is Perverse there. So we first do a partial compactification before taking quotient by gamma. So basically, we have, as we saw right up there, D is NP cross AP cross NP, and I'm going to DP. Thank you. And I wrote it there for the maximal parabolic, but I have the exact same formula for any of the parabolics. And I should have said any P equals GP standard G inverse, where G is a rational element. So you take all of these standard parabolics, those, and you could have more than two GI primes, and that gives you the standard ones, and then you conjugate them all. Those are going to be all the parabolic Q subgroups. So for any one of them, you have this Langland's decomposition. When you mod out by the maximal compact, again, this turns into a DP, although it's going to have more factors there. And you embed this into something you can call dp, which is just np cross ap bar cross dp. So what's the ap bar? That's these one-parameter subgroups are showing the directions in which we're compactifying, which we're adding something at infinity. So remember AP, well, in one case over there, it was a single copy of the positive reals. Here it was 2 copies. In general, it'll be R copies. And you embed that into R copies with each copy having an infinity at the end. And you put this on in a real analytic sense, you use a coordinate. If A is your coordinate here, you use the coordinate 1 over A at infinity. And this, by definition, is AP bar. So you just stick that in. That gives you the, quote, corner at P. And then you set dP to be the union over all P of dP. And of course, you got to be careful. For 2 different parabolics, these d of p's will intersect, and you have to carefully work out what the transition functions are. But that's dp. And another way you can think of it is it's a disjoint union of over p of np cross letting all the coordinates here go to infinity, infinity to infinity, cross dp, and do I have a notation for that? No. Yes, of course, the classical notation, this you could write as E of p. So this is a partial compactification of the symmetric space. So imagine the upper half plane. Upper half plane, one of the parabolics are upper triangular matrices. As you vary the AP here, you're simply going up in the vertical direction. And this is trivial. This is the real line. And so what you're doing here is you're adding another horizontal real line. Here's the upper half plane. You're adding a line up there that you converge to here. But if you conjugate that parabolic, say, to the parabolic that's stabilizing 0, then these horizontal lines, which come from the unipotent radical, turn into horocycles. And so you have this stuff coming into that cusp, but what you do is you essentially cut that out and you add in an entire line, entire real line instead of the origin. And you do that for every rational point at the bottom. So it's not a locally compact space.
In this last line in the bottom,
Yep.
don't you want something like any subset of the entries are infinity and then the other ones are not infinity?
No,
You
no.
want them all simultaneous?
All simultaneous infinity, because notice, here is a union,
Right.
here is a disjoint union.
Right.
So I'm going to draw this picture more in a moment, but basically, over at a corner, okay, D of P, where I've included all of AP bar, is going to have all of that in infinity. But what I'm putting here is just that dot. This stuff that's infinity is going to be gotten by a different parabolic, a maximal parabolic. We'll have all of, and that's that thing I was saying about you have to, for 2 different parabolics, P contained in Q, you have to understand how these coordinates transform from one Langland's decomposition to another. I've always used P, but you know, if you have different P's, these are different factors, right? So this is for a maximal, this is for another maximal, this is for the minimal, and that's what's happening here.
And so points that are not at infinity for one P are at infinity for another one. Is that correct?
That's right. That's right. This is basically what this is. This is a disjoint union giving you all the different strata. When P is actually equal to G, you're getting all the interior. When P is a maximal, you're getting this, but not that point. When P is another maximal, this, and then one lower down here. So in this case, for the upper half plane, every parabolic is either G or maximal, so one of these terms is the entire interior, and all the other terms are just real lines that are being glued in the appropriate way. Good, thank you. Other questions? Okay, so now to define the Borel-Sayre compactification, you just take this partial compactification of the symmetric space, and you notice that the action of the rational points of the group on D actually extend to all of these things here. So I can still take quotient by my arithmetic group. And what do I get? I get, if I write it as a disjoint union of its strata, the strata, so now P, these are now representatives of gamma conjugacy classes of parabolics. Because if you have one parabolic, it's going to have this thing at infinity. If you take a gamma conjugate of it, there will be a different thing at infinity, but that gamma will take this guy isomorphically on the other, identify them. So no longer do you go over all parabolics, it's always gamma conjugacy classes, or gamma orbits. So, and what do you get? Well, you get, so it's called, let's write yp. And what's the structure of yp? Well, here's the thing that's out at infinity. So yp is going to be np, and I'm going to leave off that power of infinities, cross dp. And what do I have to quotient it by? Well, if gamma conjugated p to be some other parabolic, I don't have to worry about that. I just need to know the gammas that conjugate p to itself. Well, that's going to be the same as gamma intersect p, because p is its own normalizer. And what is this going to look like? It's going to be a fibration. It's going to fiber over, well, first of all, what are the fibers? It's this unipotent radical modulo gamma intersect the unipotent radical. And this is going to be compact, a compact nil manifold. So those directions that were decaying in the metric, in the locally symmetric metric, they're going to be tangent to a certain compact manifold that is shrinking down as you go to infinity. And that's going to be over dp, essentially mod gamma intersect mp. There's a little bit of a lie here. I'm going to write this as xp. It's another locally symmetric space. So at infinity in Borel-Sayre, of one locally symmetric space will be strata. The strata are nil manifold bundles over other locally symmetric spaces. And the reason it's a flat bundle. And the reason it's a bundle, not just a product, of course, is because the groups underlying these two factors don't commute. There's a conjugation action of MP and AP on this NP. So, I've got to draw a picture of the corner now. So that's the Borel-Sayre compactification. Before I very briefly indicate the others, I have to draw this picture because it's been said that it deserves one of those Bourbaki dangerous bend signs, right? And I can't remember which way the squiggle goes. So. So let me draw the picture of the corner. In the case of SP4, okay, so here's the interior. So we have one parabolic, one maximal parabolic up there. This is the one, well, actually, I'm drawing this picture before I take the quotient by gamma, but that's okay. So this is y. No, I'm sorry, after I've taken the quotients. This is yp1. So this is when g prime equals 1. And I don't have that anymore, but basically when g prime is 1, there's an sp2 in the center, and for sp4 there's nothing else. And then we have, for the other parabolic, this is when g prime equals 0. This is for g prime equaling 1. So for g prime equaling 0 over here, that central square is sp0. It's trivial. And what you get on the higher square is a copy of SL2. So this is fibered over, let's see, what this space is. Well, as I just said, it's sp2, so that's going to be a1. But I'm going to write it point cross a1 because there's no linear term. And this guy is fibered over the upper half plane modulo SL2Z cross point. Now, these are both the same thing. sp2 is the same as SL2, but it's fundamental to treat them differently, as we'll see in a moment. Okay, but that's not the main thing I wanted to say here, is the following. Let's look at this corner. This is yp0. So this is where the actual corner is, and here's that A2. I'm going to draw that. And that is that coordinate. I think I wrote it A1. This is this coordinate A2. And so using this picture here, basically there's a nil manifold bundle over all of this area, but the only thing that's left is this product of two copies of the positive reals. There's this 6 minus 2 is 4. There's this 4-dimensional nil manifold, and there's this 2-dimensional R plus cross R plus. This is trivial. But here's the thing. Using the Langland's decomposition, there's a Langland's decomposition for every parabolic. Using the Langland's decomposition here, there was also a split guy, and here is what happens as you go off to infinity. But that Langland's decomposition also allowed you to take this thing at infinity, and if you plugged in something other than infinity in that AP spot, you canonically could bring it inside. Canonically up to the choice of what point you wanted to go through. So this is a copy, a canonical copy of YP1. Canonical up to the fact that I could shift it up and down. And the thing that you have to understand here is that when it hits there, it doesn't go to here. It comes down. And similarly, there's a canonical copy of YP0 here. YP0 inside. That doesn't go up and hit that boundary face. It comes out there. And the reason why, well, the reason why is, well, so here's you have your A sub P1, and you had that coordinate A I was looking at. So warning, A, the coordinate A on AP1 in the Langland's decomposition here is not equal to the A1 function on this AP0. It's actually equal to A to the 1/2 times A2. And this is because what's behind all of this is the root structure of the Lie algebra, and the root structure is type V2, and the two roots are not orthogonal to each other. So this angle is an acute angle. This is not just the picture. That's in the space. The angle here doesn't make any sense, but this is essentially a parallel pipette, so I've drawn it also as acute. But this thing is coming down and cutting through like that. Similarly, the A on here is not the A2, it's actually A1 times A2. So this makes it very tricky when you're working in corners.
Is that corner
Yes.
YP001?
I think you want to go something.
Say again?
The corner corresponds to null.
The corner is YP0, which is equal to
Give another YP not.
Yeah, the other side.
YP01. Okay, which is a nil manifold fibration over a point. No. Yes. Yes. Question? No. Okay. So now let me introduce the other two compactifications, and that can go very quickly. I feared I'm running out of time, but I can say a few things at the end. If I have enough chalk. So, what about reductive Borel-Serre? Well, we had X bar, and it's not up anymore, but that was a disjoint union of strata, which I wrote as YP, P belonging to gamma conjugacy classes of parabolics. And these guys were vibrations over the XPs, and the fibers were exactly the tangent vectors to the fiber are exactly the vectors that are going to 0 as you go out to infinity. So what you do is you collapse those fibers. So you take XP, you have a collapsing map here, and take this joint union. So that's the map here. And now, from that formula I gave you for the metric, clearly the metric extends to each XP. It's a little more complicated, but not too much more. Here's the picture of it. It's the same picture in that the combinatorics of the faces are the same as over there. This is X bar. But things are being collapsed, so what I should draw is, for any point here, it's only being collapsed at infinity, that nil manifold, so there's that nil manifold and it's coming in. Here's a different nil manifold coming in there. And over here, there's a higher dimensional nil manifold that partially collapses here to a circle and then partially collapses there to a different circle. Remember now, that line and this line, they're basically upper half plane mod SL2Z. So the neighborhood of the cusp point is going to be a circle across a half line. And there it is, there's that one circle and there's the other. But then there's this larger 6 minus 4, that doesn't sound right. Yes, there's this larger three-dimensional torus that's in there. Cross a line. This is a three-dimensional iterated S1 bundle. Cross an interval, but then with parts, two different collapsings taking place at the two different ends. So that's how you get to a compactification that makes the most sense for differential geometry. And now if you want to do complex analysis or algebraic geometry, you want to go to the Bailey-Borel compactification. Well, remember each XP had, in essence, a product decomposition, XPL cross XPH. It's really a fibration, but modulo a finite group. I can write it as that product. The point is that the complex structure from the inside, when you bring it out to infinity, leaves this invariant, but takes these directions and pushes them inside or up into that nil manifold fibration. So if you want to have a complex structure, you can only keep these. So that's why this copy of the upper half plane is going to survive. This copy of the upper half plane isn't, because the complex structure here does not extend to the complex structure at infinity. And so you take product over P dagger of just the X P dagger H's. So you just project this onto this. You can have different P's that have the same XPH. So the indexing set here is different. And so let me draw it right there. If I erase that, here's X star. Well, so that's a stratum at infinity. This is a link that only hits that stratum. This dotted line is just because the link is coming out and coming back again. And there's the other stratum. That's a 1. That's a 2. This is a 0. So that's the Bailey-Borel compactification. Okay, where was the question? Yeah. Oh, that's the theorem. So, yes. So I'm just trying to motivate. I'm not proving anything. So I motivated why this made some sense, if you were willing to believe me. So Bailey and Borel, in a very long paper in the Annals, using automorphic forms, shows that there's an embedding of the A2, or rather general, into a projective space such that the closure of the embedding is this compactification, and that it's a high power of the canonical bundle. But that only gives it to you that this is a projective algebraic variety defined over some field. Other work showed that it was actually defined over a number field. And that's important for Langland's program. I'm out of time, so I'm going to really have to stop there. I'm happy to take more questions, but thank you.
Questions?
Yeah.
So you can compute the L2 cohomology of some of these spaces? If yes, how?
Yes and no. So the theorem, there are two theorems about this. So first of all, L2 cohomology, the way I'm thinking of it, is an invariant of a Riemannian manifold. Okay? So the only Riemannian manifolds here actually are the interior. So these all have the same interior with the same metric. So there's only one L2 cohomology. And what the theorem is, this was conjectured by Zucker, and then it was proved in general by myself and Mark Stern, and independently by Edouard Loinha, about exactly the same time, that the L2 cohomology of the locally symmetric space with coefficients in any metrized local system coming from a representation of the group is a topological invariant of the Bailey-Borel compactification. But it's not the ordinary cohomology, it's the so-called middle perversity intersection cohomology of Bailey-Burrell. So this is a topological theory that can be defined on a wide class of stratified spaces. And the nice thing about it is that whereas for ordinary cohomology, Poincare duality fails when you have a singular space, middle perversity intersection cohomology retains Poincare duality, which makes sense because this is finite dimensional. It's represented by L2 harmonic forms, so you have Poincare duality on the left.
How do you prove this?
Well, it's not easy. I've proven it twice, once with Stern and once another way. Basically, you have to pick any point, so I haven't had time, but the good thing about this is that this is characterized by certain local conditions. The bad thing is, well, here's a point. I need to understand the L2 cohomology locally here. Unlike all the other pictures, this link is quite complicated. This link is a fibration over another locally symmetric space. And I should emphasize here that I gave you formulas for a metric showing that it's a multiply warped product here, here, and here. The metric is not it's not conical, and it's not a multiply warped product. And that all comes down to this issue I said about these things coming in. So so this neighborhood is this. And so if this corner wasn't there, that's a warped product metric, and there are methods. It's not easy, but you can deal with it. But here you have to rescale this to put it there. That changes the metric out near infinity. And so you have to do some fairly subtle analysis to break up. You have to calculate L2 cohomology of this. You do that by breaking it up into different regions, one near here, one away from there, doing some analysis in both, and then very carefully patching them together using cutoff functions with very, very, very small derivatives. But fortunately, it's a complete metric, so this point is infinitely far away from that point, and you can do it. So this was done around 1990 in papers in the Annals. I gave a later proof that worked actually up on the reductive Borel-Sayre, and it's not easier, and there's a lot more combinatorics, but in some sense, the local calculation is easier.